Good morning. Today we are going to study Viterbi algorithm. In the last lecture, we learned about the maximum likelihood decoding, and the principles are same in this algorithm also. That only we have to study about the theoretical nuances. That the problem of optimum decoding is basically to find the minimum distance path from any initial state back to the same initial state. So in this diagram, you can see so many states and the initial state is S0. So we want to come back to S0 after traversing all possible states, and the minimum distance path will be considered the Viterbi path or the best path. So the minimum distance is the sum of all path matrices, and we have introduced path matrices in terms of Hamming distance and in terms of weighted path matrices in the last lecture. So for the sake of simplicity here, we will consider that the Hamming distance itself is the path metric in this particular example. So if our received code sequence can be given as y subscript j and decoder's output sequence for any given mth path can be written as x subscript m j, then the conditional probability associated with it summed over all possible values will give you the minimum distance path in terms of a joint probability. So we have this relation log of pyxm is equal to summation of pyj upon xmj, when pyj upon xmj is a conditional probability which gives the likelihood, given that decoder's output sequence for the nth part is xmj, what is the received code sequence. We want to ascertain the likelihood of it, so that is maximized by the correct path. So it is basically an exhaustive search mechanism, and which gives you the computationally intensive method for searching all the paths in the phase trellis, the trellis diagram we have talked about. However, we want to avoid this exhaustive search, and because in exhaustive search mechanism we have 2 raised to power k paths emerging from 2 raised to power l plus 1 states for a given nkl code. So that is going to be a daunting task, because whenever the nodes will diverge, the computational cost associated with finding the maximum path will increase exponentially. The Viterbi algorithm is an alternative for this exhaustive maximum likelihood method, and it gets into efficiency via concentrating on what we know call as survivor paths of the trellis. So in order to understand the concept of survivor path, we need to take an example, and we need to have a look at a typical trellis diagram. So we have this trellis diagram, and assume for simplicity that we have a convolutional code with k equal to 1, and for k equal to 1 we can have at most 2 raised to power k equal to 2 branches which can enter each state in the trellis diagram. So we have only a naught as the state from which everything is diverging. Now we assume also that the optimal path passes through node S, the capital S. So metric comparison is done by adding the matrix of S into S1 and S2. At the survivor path, the accumulated metric is smaller. Otherwise, the survivor path would not be the optimum path. So for this reason, the non-survivor part can be discarded or deleted. So we are left with a little calculation which can be done only with the survivor path. So note in principle that the whole transmitted sequence must be received before decision. However, in practice, we can store states for input length of 5L, which is quite adequate. Now, we would like to have a conceptual understanding of the survivor path, what we want to do with the survivor path and how we can understand it conceptually. Suppose this node A naught at the left side of this slide correspond to a city in the western border of our country. Let's call this city Amritsar. We want to go to one of the 4 cities on the eastern part, like Calcutta, Guwahati, and Bhubaneswar, and Vizag. These 4 cities are on the west side, eastern side of our country. So we are going from a city in the western side to city on the eastern side, and it is going to take us 3 days to reach there, and each day can be uh, considered equivalent to a node while going from left to right in this trellis diagram. So let's call the traversion from node A0 to A1 as day 1, from A1 to A2 as day 2, and A2 to A3 as day 3. So if I ask you a question, what is the minimum distance path for in going from A0 to A1 to A2 to A3 or to B3, C3 and D3? So if after arriving at node say A2, I know that the best path was from A0 to A1 and then directly to A2, and any other path was not feasible in terms of the length, then we can discard all those paths. So only those paths survive for which we know definitely that it is going to be a minimum distance path. And that is the gist of this survivor and non-survivor path comparison. The same thing we are going to do by applying our prior knowledge at a given node, that while coming from one node to another node, only these paths are applicable and these can be deleted. Now we will take an example that the received sequence Y is given on your screen, and the NKL212 encoder, we have seen how do we encode a convolutional code using some modulo 2 adders and register stages. Now we need to determine the Viterbi decoded output sequence. We need to note that for this encoder the code rate is half and memory depth L is equal to 2. Okay, so we will construct this trellis diagram for this given received sequence. Again, compare this sequence. What was it in here? 0 1 1 0 1 1 1 1 0 1 0 0 0 1. So here also the received sequence is written in this diagram: 0 1 1 0 1 1 1 1 0 1 0 0 0 1. So from looking at this trellis diagram, and if I extend my discussion on the survivor and non-survivor path, taking the example of traversing between particular cities, we can see here that if we know that starting from this city and coming to another city takes the minimum amount of time, we can eliminate other possibilities. So the decoded maximum likelihood code sequence is 11101011000000. Why this is the decoded sequence? Because Hamming distance corresponding to the received sequence is 4 and the respective decoded sequence is this particular thing. This minimum distance path in this black circles denote the deleted branches, and dashed line indicate that a 1 was applied. Solid light indicates that a 0 was applied. So these branches were deleted, where we have indicated this with this black circles. These branches were deleted because the path metric at that point was above a particular threshold. It means it was not the optimal path. It was not the minimal path. It was not the minimal distance path. Now, in the previous example, it was assumed that the resistor was finally filled with zeros, thus finding the minimum distance path. In practice, however, with long code words, zeroing requires feeding of long sequence of zeros to the end of the message bits. This wastes channel capacity and introduces delay. To avoid this path, memory truncation is applied. What we do, we trace all the surviving paths to the depth where they merge. Then we can understand with the help of this figure that this figure shows a common point at a memory depth j.